Without further ado, huge welcome, Barry, from Geneva. Thank you for giving time to our community today. And over to you, the floor is yours.
Thanks, Anne. Yeah, thank you for the very kind introduction, and it's a real pleasure to be able to speak to all of you at the Balsillie School of International Affairs. As Anne said, former Balsillie scholar, so I was in Waterloo October to December as a Balsillie scholar, and I got a chance to understand better the school and also get started on a project that will become clearer as I tell you about quantum. And I'm going to try to not just tell you about quantum, but how it's relevant to international affairs, the kinds of stuff that most of you think about. Um, and I was also working with CIGI, the Center for International Governance Innovation. And then the 3 months that I worked it was on emerging dual use technology. And then I'm not focused on quantum, but I'm using my experience and knowledge with helping quantum startup companies, helping government strategies and European Commission and other entities. And so I've been helping a lot over the last 20 years towards strategic thinking by countries to to figure out how to develop quantum and what I call quantum adjacent technologies, and also deal with security issues and a lot of stuff. And so these days I'm now working on those kinds of problems. I'm on sabbatical, so I'm taking 6 months off quantum physics. But then in April, I want to start splitting my time more. But really, I'm focused on those kinds of issues. Okay. So what I'll do, I'll just go through a bit of explanation about quantum. But I'm trying to keep that to a minimum. So I'm just trying to give you a sense of what it's about, why it's important. There's no way around the fact that it's hard to understand. And so my purpose here is not to train you to be a quantum physicist, but really to get the essence of where quantum has been, what makes it so difficult to deal with, and then why it's so important that we have policies and strategies, whether or not we understand the discipline. So we can't hide from quantum just because it's hard. We have to be able to deal with that. I'm going to try to go, let's see if I can click. There we go. Okay, so let me just give you a bit of history. And so I'll just try to explain as simply as I can what happened. The 19th century, in physics, there was a belief, Lord Kelvin, whom one temperature scale is named after, felt that physics was done, that it was just details by the end of the 19th century. But there were some niggling problems that existed, explaining the colors of the sun, which is in the upper left diagram. You see that rainbow. What is the distribution of color emitted from the sun wasn't explainable from 19th century physics. Some colors were missing, and you can see in the lower left, it says helium spectrum. Helios is the Greek word for the sun, and helium was the first element that was discovered not on the Earth, but in space. And so the idea that the sun has some distribution of intensity of colors, that some colors are missing, was all very mysterious. Over time, you can see this diagram of circles and circles. If you took a high school chemistry or physics class, you might have learned that an atom is a nucleus with electrons going around, and then they only fit in discrete ways. So there are only certain orbits an electron can take. This concept was able to explain early stage things like the colors of the sun, the intensities. And as time went on, these ideas, and so the idea that the electron only takes certain orbits, that it has certain energies, these are known as quanta. So quanta is like the word quantity, how much energy there is, and it's only discrete values. And then the upper right, there's a diagram of light hitting a metal, and the light hits the metal, electrons pop out, and whether the electrons come out depends on the color of the light coming in. Einstein got his one and only Nobel Prize for explaining that. That's the photoelectric effect. And then in the lower diagram, it says light is, and then I don't know what you see. This was done by Hofstadter. If you follow the Big Bang Theory, Leonard Hofstadter was, his surname is actually taken from the name of the father of the guy who drew that picture, Nobel laureate in physics. And so depending on how you look at it first, you can see it says light is a particle and light is a wave. And so this guy drew that picture as a way of trying to convey the essential mystery of quantum mechanics. And essentially what goes on is in the 19th century, we conceive of everything being made of particles like electrons and atoms and things like that, or waves like light waves, sound waves, and so on. And the idea that everything has this duality, that it can be light or particle depending on how you look at it, is a really deep concept. And that's the fundamental notion of complementarity in quantum mechanics. So I'm not trying to help you understand quantum mechanics, but I'm showing you the key to understanding quantum mechanics as much as possible. So that gives you an idea of the history of quantum. And then where it became really important technologically, and this comes up as I get to policy type issues, is by understanding quantum mechanics, we could understand not just how the atom looks, the electron going around the nucleus, but we could understand the nucleus, what the nucleus is made of, and the nucleus is made of particles called hadrons, and hadrons are made of quarks, and we can keep going deeper. And in fact, I'm speaking to you from CERN in Geneva, which is the place in the world where new particles are being discovered. So serendipitously, I'm talking to you from a place where the main focus of the campus I'm on is to have very smashed particles together and see what things are made of. And so as quantum mechanics and high energy physics, smashing things together, looking what comes out, developed, we unleashed enormous power, and especially nuclear power and nuclear energy. So the idea that quantum is an object of curiosity is for most people secondary to understanding and exploring quantum physics, unleashes power, and it does a lot of other things. So early on, the early control of technology was associated with controlling nuclear technology. On the good side, we get nuclear power. I'm not sure if you're pro-nuclear power, but on the bad side, we get nuclear weapons, and surely nuclear weapons are worse than nuclear power. And that's a whole debate. There's an element of mystery to it. So I want to convey to you with this slide that philosophically, there are big questions about quantum mechanics. So we don't consider quantum mechanics as a solved problem in a philosophical sense, but we do have, we can write it in a descriptive way that our understanding is good enough to do fantastic experiments and build technology. But this mystery that is pointed out here, you can see a cat inside a box, and then there's a nuclear decay. So there's a nucleus, and those four disks represent the nucleus of helium. So I mentioned helium before, also known as an alpha particle. If you did high school physics and used a Geiger counter, you would have picked up radioactive particles. And then the nucleus can decay. And you set it up so if the nucleus decays and that helium nucleus is flying out, it triggers a poison gas that kills the cat. And if it doesn't, then there's no poison gas and the cat survives. But quantum mechanics tells us because of the wave-like nature, the alpha particle is also a wave. In a sense, it's both inside and outside the nucleus at every moment, which means that the gas is and isn't released. And it means the cat is and isn't alive. And so we get what's called entanglement, that no decay, cat is alive, decay and the cat is dead. And the reason this is a big thing, and this is pointed out by Schrödinger, who this year, 2026, is the 100th anniversary of his paper in the field. Schrödinger pointed out, he said, if quantum mechanics is correct, then even the concept of life and death is no longer objective. I like to joke, in the US, they have a saying that only two things are certain, death and taxes. And Schrödinger's paradox shows that only taxes is certain, even death is not certainty. And so you can see there's, if you say, well, a consequence of quantum mechanics is even notions like life and death are no longer objectively meaningful, you can see that there are philosophical problems that emerge. And so I like to think my day job is doing, quantum science and technology, but at nighttime, I might ponder these kinds of philosophical mysteries. So I'm just sharing with you, you'll see a lot of stuff about quantum in the popular press, and everything can be boiled down to this kind of puzzle. Okay, and by the way, please interrupt if there are questions. I like the interactivity. I'll keep going, but I'm very happy for interruptions. Okay, now I'm going to try to give you an idea of how things are changing. So you get the idea that where quantum technology was really good is we understood the atom and the nucleus. On the left, you can see a periodic table. And the periodic table, that's not actually complete, but it is meant to list every atom that nature gives us. But nowadays, you can make a wish list. You say, I wish nature gave me a different atom that is not in that periodic table. And now with nanotechnology and fabrication techniques and the kinds of things that are making transistors smaller and smaller, all this kind of stuff, we're able to make artificial atoms. In the upper right, you can see some kind of circuits. They're superconducting material. So whereas in electronics, electric currents have resistance, these have no resistance. And it turns out that the way the current goes is quantum mechanical. You can make it go clockwise or counterclockwise or a superposition. You can make it go just like live and dead are no longer objective. The current going clockwise or counterclockwise is no longer objective. That becomes important because if you say like life and death, if you put things in an informational context, you can say, I'm going to call a living thing, I'll assign it a logical 0, and a dead thing is a logical 1. So if you kill something, you're flipping 0 to 1, and if you can bring it back to life, 1 to 0. We don't do that, but if you think about these electrical circuits, if I flip between clockwise and counterclockwise current, I'm flipping between 0 and 1. And I can make both coexist, and then I have a kind of logic where 0 and 1 coexist. And so there's superconductors, there's quantum dots where we have different semiconductors that confine an electron. On the lower right, that's a diamond where you have a bit of nitrogen get into it, and you can make sensors. So you basically, if you tell me, I mean, you can't always do it, but the idea is that if you say, I want to be able to sense some field. Let's say you want to invent in Star Trek, I don't know if you've seen Star Trek, but the way they do things, if they want to diagnose somebody, they just have what they call a tricorder and move it around, and it reads every signal from the body, and the doctor instantly knows what's wrong with the person. And so in that sense, if your sensor, the way I think about it, if I want to invent one, is I would say, what do I need to sense? What is the atom I need? And then I would manufacture a diamond or some kind of semiconductor structure or whatever. So once you get artificial atoms, you can start to do a bespoke or tailor designed way of detecting what you want. And so this whole idea of making artificial atoms really changes the game. And this is, the last few decades, we're getting really good at being able to manufacture things. Okay, where does it take us? One of the things that happens I'm a quantum physicist, but I'm trying to think about societal issues and so on. And so the way I think about it is quantum is 125 years of successive inventions. If you talk to many quantum physicists like to think about the future, not the past. So if you talk to most quantum physicists and they'll talk about quantum technology, they'll tell you stuff that doesn't exist because they're excited about what doesn't work yet. I'm telling a different story. I'm saying we have a whole history of quantum technologies, and we want to invent new ones as a continuation. So to a physicist, that sounds a bit boring, but in terms of national strategies and investors coming in and startup companies, it's important to regard quantum technology as a continuum that's been going on for over a century. And so I'm just going to give you an idea of what was done in the 20th century and how it's relevant. So the upper left is a nuclear reactor, the idea of making nuclear power. And Canada has been was one of the major players in nuclear power with the CANDU reactors, Canadian deuterium uranium, I think. And that's a play on nuclear physics. The middle of the upper photographs shows a superconductor levitating. So I told you about the superconductor, a material with no resistance. This was a big deal in the 1980s. Countries like Japan invested. The hope, which didn't pan out, is that you could make superconducting rails and then run monorails on top. So you could, you know how a train runs on the rail, a railway. If you could levitate your train on top, you would get much more efficiency, speeds, and so on. So we're able to levitate things, and there is levitation that can be practical, but levitating trains never worked out. Where that's especially important, on the right, it says SQUID. That stands for Superconducting Quantum Interference Device. And these SQUIDs are in every sophisticated hospital. So if you go in for a brain scan and you go in this big machine and it goes ping, ping, ping because it's got a refrigerator to keep things cold, it's reading flips. So there's hydrogen atom is a proton electron, and then basically it's applying magnetic fields and reading flips of hydrogens and creates a map of your brain. And that's a quantum effect. The idea that you're flipping the spin of a proton is you have to know quantum mechanics to be able to describe it. So every hospital in Canada is using these things. Well, I can't promise every hospital, but it's common in hospitals. And then on the lower left, I don't know of a practical application. That's a superfluid, and it looks like the superfluid is dripping out the bottom, but there's no hole in the bottom. And so what that fluid does is it looks like it defies gravity. It crawls up the inside over and then goes down the outside and collects in the bottom. And so it's tunneling. It's the fluid, remember I told you about the nuclear decay that leads to the killing of the cat, Schrodinger's paradox. In this case, the fluid is effectively managing to get out of that bowl and drip through the bottom. And that's because, in some sense, the superfluid's a wave, and so it can't be fully confined. And so that's an example of a superfluid. The lower middle one represents an atomic clock. And our global positioning systems and timekeeping standards depend on precisions of these clocks. So one of the major limits to how fine we can do positioning is how precise the clocks are. And just to give you an idea, the locking mechanism we have to keep clocks precise is so precise that if you turn on your clock at the Big Bang, so 15 billion years ago when the universe arguably began, the clock would only be off. I think now it's like 100th of a second. So our clocks are so accurate we can get that. And then you can think that's crazy. Why do I need to keep track of 15 billion years of time with 100th of a second error? It's not in the typical timekeeping sense, but it determines the precision of how well you do positioning. And then the last figure is showing an application of a laser beam. And so lasers were invented, 6 different lasers were invented in the year 1960. And lasers are used for barcode scanners. If you go to the supermarket, you have lasers there, laser pointers, laser eye surgery, and so on. And the way that lasers operate is a quantum mechanical phenomenon. And I could bring up more, but my message here is that quantum technologies in the 20th century, changed our lives. And I forgot, beside the one with the eye, that's actually a transistor. And the transistor relies on an electron getting through a barrier, just like that superfluid manages to effectively go through the bowl. The nuclear decay that kills the cat is an alpha particle or helium nucleus escaping some larger nucleus, and the transistor operates that way. And these are all known as quantum tunneling phenomena. So it's very important, the quantum effects, and it's changed our lives. And we believe the 21st century, we're going to see more changes. So I told you the philosophical problems. I explained the wave-particle duality, and these are really hard, but there's no denying that our lives would be materially different if we didn't understand quantum mechanics and make these things. And now I'm going to talk about the future. So in the 21st century, we loosely talk about 3 different strategies. One on this slide is sensing measurement. The next slide, I'll talk about communication and cryptography, and the third one, quantum computing. And so this set of pictures just captures some of them. So I'm going to give you a sense of what's going on. On the far left, you see that box, and then there's a V for vacancy and A. That's essentially a diamond. Talked about diamond as a sensor. And so the idea of moving a diamond, it could be possible moving a diamond with a defect, something that breaks the crystalline carbon structure, to be able to sense things about molecules. So it might be an example of this. One that is an important use case is, if you're at the airport and you have your baggage, how do they tell what's, how do they tell if there's something in the bag that needs to be caught? And the answer is they'll have dogs walking around the baggage area to sniff. So the dog is able to sniff things the human can't. And then, if you go through the airport to through the security, sometimes they might put a swab on your computer to be able to sense certain molecules. And sometimes they'll do it to your belt buckle too, to pick up different chemicals. And so we really would like to make better sniffing technology. And the sniffing technology depends on thinking about how we can combine sensor technology with picking up certain structures of molecules. So that's an example of quantum technology we're trying to develop. The upper middle is showing you what's called a gravitational wave detector. And so historically, astronomy, looking at what the stars and galaxies are, was optical. You have a telescope, you look and you see it. Over time, we got better at microwave and infrared and ultraviolet. So areas that are light, but not light the eye can see. And then more recently, we have neutrinos. So it's some kind of subatomic particle that we detect to learn about stuff that's going on. But the 21st century has opened up gravitational wave astronomy. Going back to Einstein, space and time are curved. So there's effects that cause space to contract, time to dilate, and we're able to read that. So the 21st century has opened a window to studying the universe instead of by particles and light waves. It's by studying the curvature of space and time itself. And it turns out that a lot of the phenomena we want to detect require a precision that is if we don't do our quantum measurements right, then we're limited in what we can observe. So the whole field of gravitational wave astronomy arguably needs some quantum solutions. And then on the right, there's the diamond sensor, and below, there's ways to be able to get quantum enhanced atomic clocks. And the really cool picture on the lower right is imaging a stealth bomber. By the way, I'll talk about military stuff and we can discuss that. When I do it, I'm not some heartless person saying, here's all the military tech. It's a reality when you're doing scientific advancement that there are military aspects. So I'm putting it out there and I'm happy to discuss morals and ethics and all that if you want. But here in this case, I think of American Hollywood movies where you want to be able to, if you see, what was it, Maverick, whatever, Tom Cruise, this movie, like he's flying one of these unstable fighter aircraft, and then he knows that the enemy is locked on, right? So they sense that there's a lock on, and then once they're locked on, they have to evade missile launches. But if we can do a very weak sensing of aircraft, then the pilot doesn't even know that they've been locked onto. So this is representing a single photon sensing. So you just hit the aircraft with one photon at a time, reconstruct the image, and the photon at a time, so it's a particle of light, is too weak for the aircraft to be able to sense. So weak sensing is an important area. And there's more. Okay, now let me tell you about the quantum communication area. And in this one, our whole, if you think about security on the internet, it's absolutely vital. And you see how there are security compromises that take place. People break, there's all kinds of things that happen on the internet that compromise security and compromise finances and all that kind of stuff. In quantum, we're not interested in solving every one of those problems. We're interested in solving a particular problem. And the particular problem that we think about is the communication. So typically in the cryptography world, they talk about two parties. One is Alice and one's Bob, and they're communicating. And then we're dealing with the case that somebody can pick up that communication between Alice and Bob and be able to crack what's going on. Right now, so if you go to the World Wide Web. Oh, and by the way, the building I'm in is where the World Wide Web was invented. It's upstairs. So talk about the World Wide Web, but just sharing with you that this where I'm sitting now is in the building where the whole World Wide Web was invented. So in this case, you need to have communication between points. And if you use the World Wide Web, you write something like HTTP. That's what we used to do more than a decade ago. Now we write HTTPS, and the S is for secure. And nowadays, the secure communication, if you use WhatsApp or Signal and all this other stuff, the S that comes on is a secure encryption. The typical ones would be, you see that T-shirt, that's the RSA algorithm. Actually, the one to the right with all the complicated mathematics is the elliptic curve. So it's considered the best form of encryption today. And you might enjoy learning that that was actually invented in Waterloo. So at the University of Waterloo and then associated with companies, elliptic curve cryptography, which is the strongest form that's used by for national security communication, is a mathematically hard problem developed in Waterloo. And on the far left of the slide, you can see the way it works. I won't go in details. It's there if you want to ask questions. And so that's what makes that's what gives the mathematical hardness, the easiness of encrypting and the hardness and the easiness of decrypting if you have a key, and the hardness of decrypting if you don't have a key is what creates that validation of the S, the whole secure. But a quantum computer would break that easily. So part of quantum is how do we make sure that our communication is not breakable by quantum computers or some other means, which I don't go into. And now here, and since you're in international school, I want to slip in some of the international aspect. So I don't know if you've learned about Snowden, but about 20 years ago, Snowden entered a secure establishment in the US, managed to access top secret information, and then loaded it with WikiLeaks. Julian Assange, if you know or heard of him, Australian guy who was spent years in the Ecuadorian embassy in London, released it on WikiLeaks, which is no longer there. So there's a huge leak of top secret information. And I'll talk more about China in a moment because it's really important that we understand that situation. So China's has had a major priority for about 20 years, which is once in those leaks, it showed that the US had a hidden high priority to develop quantum computing. And so China then rushed very quickly to develop technology to be able to communicate in a way that would be impervious to a quantum computer attack. This slide is several years old, but it shows the lower left shows Shanghai, Hefei, Jinan, Beijing. There's Ulaanbaatar, which is Urumqi, we would say in English, the far northwest of the country. And then you can see a combination. The yellow is optical fibers underground to be able to do a long link. There's another one, Beijing to Guangzhou, which is near Hong Kong now since then, and the satellite link. And so the idea, the defense against a quantum computer attack has been a priority there. In the middle slide, it just shows how we make the quantum. So we have a way of, if I send you a pulse of light, I send you, like, if I throw a ball to you to catch, and I say, I'll throw the ball to you now or in a minute, you understand that? But just like alive and dead are no longer objective, I can make a superposition. So I can throw the ball to you in a way that's a superposition of now and in a minute. And so the pulses of light that are sent are a superposition of what we would call early and late. And some of the technicalities are there. And so that's the way they do it. They basically are sending bits in a superposition of earlier or later, or some, yeah, that's it. And then you can see in the lower right, there's the Misius satellite. Misius is Mozi in Chinese. So Misius is one of three classic philosophers. He was kind of the rational one. The satellite that's now defunct is named after, and this shows what could be called an intercontinental communication, Beijing, Urumqi, and Vienna. Technically, Europe and Asia are the same continent. So if you're a geologist, you might want to debate that, but that's the idea. So China became the most advanced country with respect to the quantum communication. As you're in Waterloo, I'll mention that the lead in China, whose name will come up later, and Thomas Yanavine, who's at the University of Waterloo, they would discuss this early on. They were both students in the same group. And so Waterloo is actually quite advanced in the technology for this area. But just and this comes down to policy issues, Canada and other countries are very slow and very cautious in their funding. And China considered it a sufficiently strong national priority that they were willing to take a lot of risk to beat the world on this. And then the other area is quantum computing. Let me just explain a bit here. The diagram in the upper left, P space, PP, BQP, all I want you to get a sense of is there's a zoology of how to categorize how hard problems are to solve. The problem of breaking elliptic curve cryptography, RSA, that I showed in the previous one, they live in the NP class, and BQP are problems that are easy for quantum computers. So it turns out that all forms of public key code breaking, so everything that keeps the internet safe, lives in BQP, which means they're all breakable. P at the bottom is problems that are easy with regular computers, not quantum. And we have these ways of taxonomy of how to do it. And so we study different problems and figure out how hard they are to break. On the right, you can see three techniques for using quantum computing. I'll just tell you briefly what they're for. I won't explain the diagrams. The upper middle is essentially a way to search unstructured data faster. But what I mean by faster is the number of calls to a subroutine, not physical time. There's a lot of confusion in the public literature about this, that people think faster means faster with respect to how long I wait for the answer. It's not that. So there's a lot of subtleties that are really important in strategic thinking. The far right is showing how to break codes. So designing quantum circuits. So designing your quantum computer to be able to crack codes. And the lower right is D-Wave, which is the first quantum computing company from Vancouver. So Canada had the first commercial quantum computers. They're looking for minima. So it's an optimization problem, how to minimize a function. And their business model is based on that. And so I put that one in. And then there's other stuff that I don't go into detail. And then the lower left just shows different technologies, different types of quantum computers. Some use neutral atoms, some use ionized atoms or charged atoms, particles of light, the photons, and various other things. So there's different ways to, superconductors, different ways to build quantum computers. I just showed you a lot of pictures because it kind of conveys to you that we don't really know we don't know if we're going to be able to make quantum computers big enough to be useful. And if we do, we don't know which one's going to win. So we can't predict the winner, and they all look very different. Okay, now I'll move away from the quantum technology to the story about where it fits the kinds of stuff that BSIA people think about. So first of all, the recognition that quantum technologies could be economically important and important in national defense, and also important for trade relations and for supply chains and all this kind of stuff becomes really important. And so a number of places, this is only a partial set, but I just filled up the slide with some flags and logos to give you an idea. Quantum SG is the Quantum Singapore. Singapore was one of the earliest countries to have a quantum strategy that they've continued to update and pursue. United Kingdom, there's Canada. Quantum Delta is the Netherlands investment currently, and Netherlands has a very strong, like, I don't know if you know, but uh, in making transistors smaller and smaller, Taiwan is the place that's the world leader in being able to fabricate. But the laser technology that allows us to etch at very fine scales is developed in the Netherlands. So Netherlands has a big quantum project that is pinned on infrastructure and expertise related with their ability to make tools that enable really fine fabrication. There's the quantum flagship, which is a European-wide effort. There's Israel. You can see China, the Chinese flag, and a demonstration going on for a quantum technology. France, Japan, India, Austria, Germany are all there. And that's a very small subset. The number of countries with quantum strategies is growing. I was over in Qatar last year and in dialogue, they buying quantum computers and doing stuff. Saudi Arabia, and lots of other places are into that. Okay, so let's just try to get a better focus on it. So I've put in the in this bluish box with white writing, it says the Collingridge dilemma. And so I just wanted to bring your attention to that. And some of the stuff here, these slides come out of work that I'm doing in CIGI. So I'm a senior fellow at CIGI, continuing to be, and I work with Tracy Forrest, Director of Disruptive Technologies. And we've had interns helping us out. And so some of the slides are drawn from a presentation that we did at BSIA last year as a seminar. So the Collingridge dilemma really underpins a problem, not just with quantum technology, but with emerging dual-use technology. So I mentioned at the outset that I'm working on emerging dual-use technology. I'm using my knowledge and experience in quantum to inform myself on a broader thinking. And so to me, I look at quantum as being emerging dual-use tech. And so some of the things in this slide have lessons beyond quantum. It could be for ASI, which is artificial superintelligence. It could be for tissue on a chip. There's all kinds of really disruptive, interesting technologies that are coming along, and they have similar challenges. And so the Collingridge dilemma captures part of this issue. So on the one hand, until we fully develop and use our technology, we can't say what the impact is. On the other hand, by the time we develop and use it, the power imbalance occurs where the technology becomes entrenched and we can no longer control it. So the Collingridge dilemma refers to what I think of as an emerging stage and this is a big dilemma. How mature does a technology need to be before you put in place security considerations, investment? How do you balance paying for it for defense versus an economic development paradigm and so on? And in that context, you can see here, so in this global scan, NATO has a quantum technology strategy. Science, which is a top science magazine, talks about quantum technology governance, standards first approach, and there are people doing research on governance of quantum technology. The OECD, that's an April 2024 paper, but they had two more papers out in December 2025. That says framework for anticipatory governance of emerging technologies. Part of OECD's function is to help member countries that's numbered in the 40s help develop these strategies. I was over with OECD in South Korea last year as the South Korean government was developing a quantum strategy. So the OECD is helping to develop this framework for how to be able to do it. Anticipatory governance is really important. Part of what the work I'm doing here in Geneva is with GESDA, where I was today for a while, the Geneva Science and Diplomacy Anticipator, and the idea of how do you do multilateral governance in an anticipatory fashion, recognizing essentially the Collingridge dilemma is interesting. Here at CERN, which is primarily a particle physics establishment. The Open Quantum Institute, which was born out of GESDA work, and I helped found it, is now here at CERN, and it's an open quantum institute. And the idea is to keep things open, but it's very interesting, and I can answer questions about that. But exactly what it means to be open is not totally clear. And certain countries and companies are opposed to open, not just because of corporate profit issues, if you like, but also how it affects security. So as we move away from a world of, unfortunately, a world moving away from international liberalism towards a multipolar, geopolitically tense world, OQI, which I'm sitting in right now, over the 3 months, is a very interesting test case to see how far we can push open, subject to oversight, some of which is transparent and some of which is not. And so I'm just trying to give you a sense of the difficulties here. And I mentioned emerging dual use technology. Let me just explain a little bit what that means. So emerging is really about this idea that technologies are so early stage that we're in the Collingridge dilemma era where we don't know if we can build it. We don't know quite what it's going to do. So it's emergent. The dual use aspect traditionally is a civil military dichotomy. So we can say, is it civilian, like is the use civilian versus military? And for a long time, especially I've been involved with European Commission for quite a while. It's like they'll fund civilian, but not military. So there's a long tradition of saying we support military, not civilian, or defense areas support military use. And it's no longer a dual, a dichotomy in there. And it's interesting, it isn't. I was just in a discussion about Hegelian philosophy. So if anybody knows about Hegel's work and idealism, you can go back to I don't know, 18th, 19th century philosophy and question whether dual use was even a well-founded notion. But we have it. Some of the work I'm doing at CIGI with Tracy and Skylar Duggan and Sabrina Chen, who were interns on this, is we're trying to get a sense of dual use in all the different ways it comes. So like within Canada, as we look at the dual use, instead of civil military, we might talk about resilient versus vulnerable. We might talk about a benevolent, malevolent dimension. We can talk about legitimate, illegitimate, legal, illegal. And so dual use is really a very loaded term that we're trying to deconstruct. And then technology is really a case of creating new objects with new functionalities based on scientific principles and methods. Okay, now I just wanted to put this document out there and give you a little bit of history on why quantum technology is especially interesting as a study in trying to understand this emerging dual-use technology challenge. And so this company Strider in 2019 issued a report. And Strider, essentially their customer is the CIA, and they do a combination of web scraping and machine learning to efficiently construct reports, which I don't think are entirely correct, but it does inform the intelligence community, that at least it has. And so their first report that was done for a fundraising, like a startup doing a raise, was on data dominance. And so I'm going to show you how this works and the thinking of quantum technology in a geopolitical setting. And so their first report that came out is meant to scare, and it's called Quantum Dragon. And it's called How China is Exploiting Western Government and Research Institutes to Leapfrog and Dual-Use Quantum Technologies. And if you get the report, you'll see my name and picture in there. So I won't go into the story here, but I'm not totally arm's length on it. But I'm make every effort to stay objective in discussing how this works. And so this became a very interesting test case in how to deal with multilateral governance. So in the report, it goes through a history. It talks about German contributions that go back 22 years. The European funding and how there's a straight line from 22-year-old funding towards, as I mentioned, like you see 2022, the micro nano satellite. So I talked about China developing technology to be able to, through the Snowden leak, to be able to attempt to make China impervious to a potential quantum computer attack on communication. And this report is going through what's argued to be a straight line from European funding. And you can see they put in a picture of 500 euro notes towards that satellite launch. And so the question that was started is this international liberal view of everybody sharing technology and science good, or is there a leak of knowledge and expertise that's leading to benefiting an adversary should there be some kind of military confrontation? And this article that came out, which created a big fuss, this came out a couple of years ago, Politics Germany, China's Quantum Leap Made in Germany. So it says Germany's oldest university in Heidelberg hosts many scientists conducting groundbreaking research. And then this article in Germany, which really shook up the German strategic thinking on quantum and other technologies, is that the development the Chinese developments are made in Germany. And also from a US perspective, Germany became a questionable country for doing full throttled research collaboration. So, and there's lots of literature on this. I can answer questions. Meanwhile, and you can see this is not that old, like this is 2023, so 3 years ago. This is from the Center for Data Innovation, and they're talking about the US approach to quantum policy. And it says the government's interest in quantum technologies dates back to the mid-1990s. And then it goes through the history of it. It talks about a National Science Foundation workshop. And so I don't know, there's more to the article and I have that. But I'm just trying to warm you up to that idea. And then gradually, this is in 2024. And so this is out of the Bureau of Industry and Security. And so in May 2024, it says Commerce, so it's referring to the Department of Commerce, adds 37 PRC, this is People's Republic of China entities, to an entity list for enabling PRC quantum and aerospace programs and aiding companies that were aiding Russian aggression in Ukraine. And so quantum scientists and quantum research centers I know in both China and Russia were put on this list. And so over time, it's become how to separate to make sure that these entities are listed and to cut off any kind of funded collaboration, any kind of exchanges. So we're seeing this partitioning between countries' programs in ways that aren't fully understood. I'll just mention here that sociology, there's a question of, you think of science and technology, but there are arguments that, what's his name in France? Latour, who wrote Laboratory Life and other stuff. Like you have these questions, is science and technology distinct, or in some actor network theory perspective, are they intertwined? And so if you take a technoscience perspective, trying to separate science in different countries becomes an impossibility. These concepts go into this kind of siloing of activity. So actually, I'll jump here for a moment. Where did it go? I'll go here and then I'll come back. Also in 2024, you can see a New Scientist article by Matthew Sparks, which is really interesting. It says, multiple nations enact mysterious export controls on quantum computers. And it says identical wording places limits on the export of quantum computers, blah, blah, blah. There doesn't seem to be any scientific reason for the control, and all can be traced to secret international discussions. So the New Scientist article is saying, so the export control, we call it the 34-qubit export control. So it says that if you make quantum computers that have 34 quantum bits or more and perform at least at some level, you can't export those. And you can't export the technology that enables quantum computers to get that good, which has created a giant muddle in like a lot of companies that are working in the quantum computing area now have a lot of uncertainty. They're saying, well, I'm making a widget for a quantum computer. Is that widget going to subject me to export control? So There's a lot of confusion. I'll mention here too that and I've written articles on this, I don't put it here, but by the time the policy was developed, which took quite a while, you can read into it that it was meant to prevent China from catching up. But by the time it goes through the timeline for creating multilateral policy, it's too late. That the intended adversary to isolate away from developing the technology provably had technology of this capability. So even enacting the export controls arguably was pointless because it's too slow a process. And this brings a very interesting collision between the speed of emerging dual-use technology and the attempt to control. How do you control things that are emergent when they're unpredictable? So now I'll just go back and tell you what happened. So there's an agreement called Wassenaar Arrangement, and the Wassenaar Arrangement was set up for nuclear technology. It's named after a town in Netherlands where the first meeting took place, and the idea is to have some arrangement that would have controls over nuclear technology. And if you follow the US and Israeli attack on Iran, the bombing of nuclear facilities, so Iran will argue certain capabilities that are sub-threshold, means that they shouldn't be a threat, and the US and Israel assess, and the Atomic Energy Agency and so on can assess that Iran has passed the threshold where the technology becomes a threat. And so the idea of the Wassenaar Arrangement is to be able to recognize that capability and then to be able to control, saying you can refine your nuclear stores to some level, but not beyond, because the timeline to build a nuclear bomb is shorter or longer, right? So that's the kind of thing that the Wassenaar Arrangement cares about, but it's 30 years old. It requires unanimity to be able to make a decision. There's a lag time for what they consider, which factors into how you're going to control emerging dual-use technology. Nuclear is not of that type. You can manage that. The understanding of how quantum works is very limited, and they're not agile. So there's a lot of problems about whether Wassenaar works. The unanimity problem was an issue. So Spain was the place that attempted to get Wassenaar to agree on control of quantum computers, but Russia, which is a target in Russia for a long time with nuclear was a partner in developing controls over nuclear technology, but with quantum and this trilateral thing, US, China, Russia trichotomy, Russia is no longer a collaborative, well, it's no longer entirely a collaborative partner. So with Russia on board, it created problems. So an ad hoc arrangement called Wassenaar -1 emerged from 2018, that US BIS rule that I just pointed out, that with their 34 qubit threshold and restrictions on cryogenic, so cold temperatures and probes, was a way of emerged. Like the evidence is there, and there are things I'm limited in how much I am able to discuss, but you can see the timeline from the US rule and then the global domination. So the idea, which I showed here, the multiple nations enact blah blah blah. You want to get a sense of how that secret discussion took place, and so the US BIS rule is quite specific. You can then say, well, was it an international discussion that took place, or was it a US discussion that led to it, and then other countries had to adopt? And you can see it's an important issue in international affairs. What Canada adopted the standard, what happened? Was there an announcement by the US saying to Canada, here's our rule, you better adopt it or else? Or is it a collaborative effort? What's the procedure? And a lot of these things, even in Canada, are cloudy. We're not told how things work. So, if you happen to be in a position where you're getting these kinds of instructions saying develop policy for this kind of stuff, exactly how to prepare for it is not so clear. You'd have to, yeah. I'm hoping to get you to be sensitized to what goes on, but there's no manual for how to deal with it. Okay, and then I just have some stuff I'll mention. I'll skip that. I just put that there to answer questions later, but I've got stuff. Oh, yeah, this back, I showed the BIS document, and then you can see this is from 2023. BIS is in the middle of developing new export controls to thwart the progress of China's quantum computing ambitions. So this sentence in the second paragraph is kind of what I would present as plausible evidence that the collective decision through the Wassenaar -1 emerged out of a BIS development. And I said that the target is China. So in the multilateral sense, the target is not named, but in the precursor, which is what BIS said it was doing, you can see that China is the target for being able to control the tech. Okay, and then this is about NATO, and there's a lot of stuff going on in NATO at the moment. But you can see it refers to the second paragraph. You think about NATO and the traditional defense against Russia and the Russia-Ukraine war, but no, the NATO focus has been on China's capability. And you can trace some of the concerns back to that Quantum Dragon report. New Scientist article I mentioned. And then this is the I mentioned here about in the New Scientist article, although quantum computers theoretically have the potential to threaten national security, blah, blah, blah. It says it's not that dangerous yet, but it says above, while refusing to disclose the scientific rationale behind the regulations. So the whole control is not explained. We understand the controls for nuclear, but with the emerging side, it's so sensitive, they won't even tell why they made 34 qubits that. Okay. Okay, and then there's more about France, Netherlands, and then I'll finish on this one. This is the Canadian one. So you can see in Canada, the export controls go through international trade and investment, export and import controls. There's a notice, number 1129, amendment to the export control list, quantum computing and advanced semiconductors, and the details are in that notice. So the Canadian part of that is to restrict, is the upshot of that whole Wassenaar -1 agreement in Canada is it be manifested as that notice to exporters 1129. Okay, I said a lot. I'm going to stop here and happy for discussion and questions.